X-ray. The one that do this experiment and give the explanation is Compton, and we call this the Compton effect. The experiment is something like this. You have the X-ray source and you shine the X-ray to the target that can be like the carbon, and then you investigate the scatter of the X-ray, okay, from this target, and you study the pattern of the scattering of the X-ray, okay. Now, one thing that the classical physics expect is that, okay, you can have the pattern of the scattering. For example, that if you change the angle here, you may have that the intensity of the scatter of the ray that scatter from the different angle may have the different intensity, right? But what the classical physics does not expect is that the frequency or the wavelength of the light will change when the light scatter or for the electromagnetic wave scatter from the target. This is something like when the light scatter from, for example, the light scatter from your body, or the light scatter from the dust in the air. The phenomena of scattering can be seen very easily if you have the light. For example, we have the light from the projector to the screen, right? But you cannot see the path of the light. If you want to see the path of the light, you can do that very easily by you can spray the powder in front of the lens, and you can see the direction or the ray of the light. The reason that you can see the ray because the light from the projector scattered by the powder and go to your eye, and that you can see the ray. Now, if the light from the projector has, for example, green, the color is green, and when you put the powder, what is the color that you expect to see? When you put the powder in front of the projector, if you put the powder in front of the projector, you should expect to see the green light also, right? Because the light that come out of the projector is green. But in this experiment, they found that if you put the green light into the target, it's not. It is the X-ray, though it's not have the color. But if to compare, it's something like if you put the green light to the target and then you get the red light, something like that. You put the green light to the target and then you get the red light. That is the electromagnetic theory cannot explain why it happened like that. But the real experiment is not in the visible light. It's on the X-ray, so you don't have the color for the X-ray, but it means that the frequency or the wavelength of the light change after the scattering. The experimental result is something like this. Once you change the angle, this angle, it means that you measure the light ray that scatter with a different angle, and when you change the angle, when the angle is zero, it means that the light scatter. The light ray is directly. Have the same direction with the incident ray, something like this, and you have the same. The lambda zero is the wavelength of the incident ray, and you have the peak of the intensity at lambda zero. It means that the scattered light has the same wavelength as the incident light. But once you change the angle, you get the second piece. That is, the light has the second wavelength. The light has the second wavelength. Okay, and that is unexplainable using the conventional electromagnetic theory. Okay. Compton tried to explain this, and he can prove using the relativity theory. But we do not study the relativity theory here. So I will give you the final result that from the relativity theory and together, the most important, together with the concept that the photon, the quantum of light also has the momentum, and the momentum of the photon is equal to h over lambda, where lambda is a wavelength. And together, from this concept and the relativity theory, Compton gave the relation between the incident wavelength and the scattered wavelength, the wavelength of the scattered light. The difference between the scattered light and the incident light is equal to this term. Okay, we call this term h over MEC as the Compton wavelength. This Me is the electron mass. It's the electron mass, Me, and C is the speed of light. Theta is the scattering angle. Okay, and this H over MEC is a Compton wavelength. So from this equation, you can see that the difference between the scattered light and the incident light is equal. It depends on the scattering angle. Okay. This expression gives a very interesting result. If this is true, why not we can see that, as I asked you before, that from the incident light with its green and then it's scattered from the powder, why not we see that it changed the color to red? Okay. If you look at this expression carefully, you can see that this term is not depend on the incident wavelength. This term is not depend on the incident wavelength. It's not depend on the incident wavelength. It means that if you shine the X-ray, if you shine the microwave, if you shine the visible light, it will give the same amount of lambda prime minus lambda zero, right? But you can see that this term, looking at this term is a Compton wavelength which is very small. It's 0.00243 nanometer. So it means that the difference of this term is in order of this number. So the change of the wavelength is very small. What is the wavelength, the typical wavelength of the visible light? Do you know that the typical wavelength of the visible light? What is the typical wavelength of the visible light? It is about 400 to 700 nanometer, right? The visible light, the 400 to 700 nanometer. So it means that for the visible light, the incident wavelength is very large compared to the change of the wavelength. Okay, you have, for example, if lambda 0 is 500 nanometer and the lambda prime minus lambda 0 is equal to the 0.00243 nanometer. You can see that the change of the wavelength is very small compared to the incident light, and there is no effect on the incident light if the incident light has a long wavelength. So this effect will you can see this effect clearly only when the incident wavelength is short. That's why they have to work